Welcome to module 11. This module is about continuous and absolutely continuous random variables. If you recall the last module, in last module I introduced the concept of a discrete random variable, and this categorization, which is in terms of discrete random variable, continuous random variable or absolutely continuous random variable, is being done based on the properties of a distribution function. So in the case of discrete random variable, we saw that if your distribution function is such that the whole weight is given to discontinuities of fx, then we call such a random variable to be discrete. So what you do is to look at whether a random variable is discrete or not. You look at the distribution function, you look at the all discontinuity points of distribution function, call that set as dx. If probability that x belongs to dx is 1, you call that random variable to be discrete. Now, based on some other properties of distribution function, we will categorize a random variable to be either continuous or absolutely continuous. So, to begin with, I have a random variable x, which is defined on a probability space omega p, and suppose fx is the distribution function of x. I will say that the random variable x is continuous if its distribution function is continuous on real line. So a continuous random variable is the one for which the distribution function is continuous at all points of the real line. I will say that my random variable is absolutely continuous if there is a non-negative integrable function fx such that your distribution function can be written as definite integral of this function fxt. So fxx is same as minus infinity to x fxt dt. Now this function fx is called the probability density function of random variable x. Now let me define what do you mean by a support of random variable x in the case of absolutely continuous random variable or continuous random variable. It is collection of all those points in real line such that fx x plus epsilon minus fx x minus epsilon is greater than 0 for every epsilon greater than 0, which is equivalent to saying that this is a collection of all those points such that probability that x takes a value in some neighborhood or around x is positive. If you look at this condition can be interpreted in a loose sense in the following way. It is a collection, Sx is a collection of all those points x such that the distribution function is strictly increasing in some neighborhood around epsilon. Now that neighborhood may be on the right side of it. It could be from x to x plus epsilon, or it could be on the left hand side x to x minus epsilon. So as long as there is a neighborhood around a point x in which the distribution function is strictly increasing, that point is taken to be a point of the support of x. Now note that we have said if distribution function can be written as definite integral of some non-negative integrable function of fxt, then my random variable is absolutely continuous. Now note that suppose fxt is a PDF. Now if I change fxt at finite number of points, you know that if you change the value of the function at finite number of points, the value of the integral doesn't change. So what this suggests is the PDF is not unique. So if there is a PDF, I can find many variants of that PDF. For example, let us look at this distribution function. fxx is equal to 0 if x less than 0, x if x is between 0 and 1 if x greater than or equal to 1. Now one can look at fxx in this case can be written as minus infinity to x g1t dt, where g1 function is given like this. One can easily see this. Why? Because note that if x was less than 0, in that g1 is 0, so fxx would be 0. So fxx is 0 if x less than 0. If x is between 0 to 1, then g1 is 0 up to minus infinity to 0. From 0 to x, it is 1. So when you integrate 0 to x, 1 dt, you get x. So x, if it is between 0 to 1, fxx as x. Now if x is greater than or equal to 1, then the whole range of g1t is covered from minus infinity to x would be same as 0 to 1 g1 x dx, and 0 to 1 g1 is 1, so this becomes 0 to 1 g1t dt, which is 1. So for x greater than or equal to 1, fxx would be 1. So this is a PDF. But note that if I change the value of this function at finite number of points, this integral is not going to change. So I'll get the same distribution function. So that means if I change g1 at finite number of points, I still get a PDF. So that is what I do. What I do is I change its value at 0 and 1. At 0 and 1, I make its value from 0 to 1. So that is what I have done over here. So this is also a PDF. So the above example suggests that the PDF is not unique. Note that probability mass function was unique in the case of discrete random variable. Now suppose I have to find the support of this random variable. So I try to see what are the points such that in the neighborhood of that point the function is strictly increasing. So suddenly any x less than 0 will not do. Any x greater than or equal to 1 will not do because it is a constant function. But if I take 0, x is a strictly increasing function for x greater than 0, so 0 is included. Anything between 0 to 1, x is a strictly increasing function, so that is included. 1, if I take a neighborhood of 1 on the left hand side, I get x, which is a strictly increasing function, so 1 is also included. So my support becomes Sx equal to 0 to 1. So it is a closed interval 0 to 1. Now note that your PDF satisfies the following properties, that it is always non-negative. If you integrate PDF from minus infinity to x fxx dx, which will be same as limit x going to infinity of fxx, which is same as fx infinity, which is same as 1. So my PDF satisfies these two properties. Now it can be shown using advanced arguments that any function which satisfies these two properties, which are that it is non-negative and total integral is 1. Such a function is a PDF of some random variable. Now let us recall our fundamental theorem of calculus. According to that, since my fxx can be written as minus infinity to x fxt dt, x belonging to R, and fundamental theorem of calculus says this definite integral is always a continuous function of x. So what this suggests? This suggests that any absolutely continuous random variable is always continuous, because your distribution function for such a random variable is always continuous by fundamental theorem of calculus. Now converse may not be true. So there are random variables which are continuous but not absolutely continuous. Now such random variables are difficult to handle and will not be studied in this course. So we will not deal with such random variables in this course. So in this course, whenever we will deal with continuous random variables, mostly they will be absolutely continuous. So that means their distribution function would be minus infinity to x fxt dt for some non-negative integrable function fx. Now note that your distribution function is determined by the PDF fx, because your fxx is same as minus infinity to x fxt dt. So that means if you know the PDF, you know the distribution function fx. And if you know the distribution function fx, you can study the induced probability space px. So this suggests that to study the induced probability space px, it is enough to study the PDF. And that is why studying PDF is so important. It is first of all a simple function, very simple function to handle with. It is non-negative and total integral is 1. And through the study of PDF, I can study the induced probability function. Now note that fxx is same as minus infinity to x fxt dt. Again, if I use the basic knowledge of calculus, if fxx is differentiable, then the derivative of this is nothing but this function fxx. So wherever fxx is differentiable, my density is nothing but the derivative of the distribution function for the absolutely continuous case. In particular, I know from fundamental theorem of calculus that if my PDF is continuous, then this definite integral would be differentiable. So this suggests that if my PDF is continuous at x equal to x naught, then the distribution function is differentiable at x equal to x naught by fundamental theorem of calculus. Not only that, the derivative of distribution function at point x naught gives me the density at the point x naught. Now, in this course, we will mainly deal with only those absolutely continuous random variable whose PDFs are continuous everywhere except at finite number of points where it has jump discontinuities. What does jump discontinuity means? That means the left hand limit of the function at every point exists, right hand limit of the function at every point exists, the left hand limit of the function at every point exists, they may not be equal. That is the only thing. That is how the discontinuity is coming. So, the left hand limit and right hand limit always exists, and such points of discontinuities are called the jump discontinuities. So, what we will assume throughout in this course is our PDF is such that it is continuous everywhere except possibly at finite number of points, which could be x1, x2, xn. Now, if my PDF is continuous, then by this relation fxx has minus infinity to x fxt dt, this says that my distribution function will be differentiable at all the points except at finite number of points, and I am calling those finite points as, let us say, x1, x2, xn. And wherever my PDF is continuous, the value of the PDF is nothing but the derivative of the distribution function. So, in such situations, we can take my PDF to be the derivative of the distribution function if x does not belong to x1, x2, xn, and 0 otherwise. So, what you will see in this course is mostly my PDF is such that it is continuous everywhere except at finite number of points, and those points also it has only jump discontinuities. Now, such functions are called piecewise continuous. So, what we will assume throughout in the course that my PDF is piecewise continuous. That means it is continuous in pieces, and it has only finite number of discontinuities, which are the jump discontinuities.